Summary of Tableau 12. A potpourri of titillating applications. Part 1. Central tendency. Stock portfolio selection and the curious case of Sir Cyril Baird, psychologist. Independence weaves a magnificent path through the subject. It crops up most naturally in the concept of a random sample, that of repeated independent trials, say x1, x2, x3, and so forth. Suppose X is a typical exemplar of the underlying chance experiment which is being repeated ad infinitum. Let us say that X has a probabilistic center of mass and expectation, let's call that mu, and that X has got an expected squared spread, a variance sigma squared. Now, as you've seen repeatedly, sums play a critical and important role in the entire theory. And so naturally we hasten to form partial sums. S1 is just x1, S2 is x1 plus x2, S3 is x1 plus x2 plus x3, and so on, Sn being the sum of x1 through xn. And much of the basic theory devolves around the analysis of such accumulated sums of independent variables. Now, in this context, it is important to view things at a proper location and with a proper scale. So accordingly, we take a sum S sub n and normalize it to form this normalized version we call Sn star. And what is Sn star? It locates Sn properly at its center. In other words, we relocate the origin exactly at the expected value, and then views it at a proper scale by shrinking or stretching the coordinate axis in such a way that we're dealing with a dimensionless quantity, a quantity with unit spread. That is your Sn star. Now, with this as background, the key and central, the most intuitive part of the theory is the law of large numbers, the venerable result from antiquity. At its heart, it says something about a law of averages. If one stops a layperson in the street and asks, well, what do you understand about chance? You might well get a response along the following lines. Toss a coin 100 times and you'll get 50 heads. And in essence, she would be right. Of course, the mathematical codification of such an answer is given on your screen. What we are really saying is that if we look at the relative frequency, Sn divided by n, then that quantity, even though it is chance-driven, via a very large number of independent perturbations. Even so, this averaged quantity, Sn over n, behaves essentially like a constant. And which constant? Inevitably, the underlying expectation of the trials driving this process. Inevitably, mu. So, Sn over n is concentrated at mu. And mathematically, what that means is that the deviation of Sn over n from mu is as small as you wish, provided the number of trials becomes large enough. We've seen beautiful, subtle applications of this fundamental principle, but at its heart, it is not at all obvious. It is true that we have grown accustomed to such a statement, such of a law of averages, which works magically. And perhaps we are so accustomed to it that we don't pause to marvel at it. If you look at it again, you realize that it is saying something quite sensational, quite remarkable. We are adding many independent perturbations. Each of the elements in the sum can vary any way you like, and without regard to the other elements in the sum. What we've really constructed is a function of a large number of independently varying quantities. And nonetheless, this function of a large number of independently varying quantities is behaving, for all intents and purposes, like a constant. We've seen rich and beautiful examples of this principle. Where next? Well, even its fondest adherents would not say that the law of large numbers is particularly sharp. It is a blunt instrument. You see, we are dividing by n, and n is a large quantity. A more precise view occurs when we take a look at the expected value and magnify what is happening around it. This leads us to the quite remarkable central limit theorem. So if you view Sn, the partial sums, properly normalized, in other words, centered properly at its expected value and scaled properly to have unit spread, then this normalized version, Sn star, essentially behaves as if it were governed by a magical bell curve. The normal distribution, the normal density, emerges magically from these ruins. Quite unexpected, quite remarkable, and extraordinarily subtle. This is the one curve to rule them all. This principle is behind much of mathematical statistics, and we've seen some beautiful applications of this idea. Quo vadis? Where do we go from here? Well, a magnificent meal should not end with a single dessert. So I'd like to offer you one more tempting delicacy to titillate your palate, to tempt you to look further. This, in the next part of the dessert tableau, will take us into antiquity, an idea which was known to the Greeks and which has quite extraordinary modern reverberations. And we shall rediscover an old friend who appeared apparently serendipitously out of the rack and ruin of the French Revolution, the Poisson distribution. This is up next.